Welcome. Today's lesson is entitled Lines, and this is really just an opportunity for us to begin talking about particular families of functions. Linear functions are probably the easiest to work with, and so we'll go ahead and start with that. The good news is really for the most part this should just represent an Algebra 1 review, but we'll start to put this in the context with this particular function and other functions as we go through the process this semester. So a lot of fill in the blank here initially and just some pretty basic examples. There is a nice construction on the back side there, at least to give this lesson a little more substance. So I think if you can you get a ruler and a protractor? That would be ideal. So that'll occur on the back side of the sheet. Anyway, let's go ahead and get started. In terms of talking about lines, one of the major characteristics of a line that we refer to is the slope. So I'm curious if you happen to recall the formula for slope. Given any 2 points on the line, and that's the idea, is no matter which 2 points you select, if it is a line, the slope will be constant. And so I'm going to go ahead and just put a little m in place here, and I'm curious if you happen to remember. Be great if you can kind of beat me to it. So if you remember correctly, we refer to slope as really a relationship between the rise of the line to the run of the line. And the rise would really be the change in the y's. So y2 minus y1, and the run of the line would of course be the change in the x's. So x2 minus x1 down on the bottom. And I'll go ahead and just put that off to the side. Of course, really the rise over run. I'm sure you did a lot of work with that in Algebra 1. There's no need to really rehash this. We'll talk about slope a little more in a couple different contexts this year. But for right now, in terms of a linear function, just rise over run. In graphical terms, the slope measures the steepness of the line. So it is a numerical calculation defining how steep a line is. In application problems, and we'll see quite a bit of these as well, really what the slope represents is the rate of change. And so you'll be working with a lot of slope over your math careers, and anytime we refer to slope, really it is how the function is changing. If it is a linear function, it is considered a constant rate of change. Okay, good. Now let's go ahead and put a few things together here as we again do play just a little fill in the blank. So let's get these 4 taken care of. And let's go ahead and draw them off to the side. Just keep it nice and easy for us. So how about just 4 coordinate planes, if you would? 4 different types of lines that you're going to see. Inclining line would look like that, so rising from left to right. Declining line looking like that, of course. And let's see what's coming next, horizontal line, and of course, vertical line. You don't see too many of these. Probably a couple different types of problems that we'll be working on this year. The horizontals and verticals would come up, but obviously most of the work will be in these, inclining and declining. Okay, so if the line is increasing from left to right, the slope of the line is, and I hope you're all right with me putting positive in there. Obviously, if we're talking about rate of change, well, obviously the function is changing in a positive manner as we move left to right. If the line is decreasing from left to right, then obviously, guys, the slope of the line is negative. Same deal here. The quantity is going down as we progress through the function. So a negative rate of change. If the line is horizontal, then the slope, of course, is, and think about this one, and a couple different ways to perceive this. If it's perfectly horizontal and we're talking about steepness, I would argue that this has 0 steepness. So a true numerical calculation, I would throw the number 0 on that in terms of steepness. Also, in terms of rate of change, going from here to here, it's neither rising nor falling, so the function values are not changing, so 0. So slope of a horizontal line, of course, is 0. And then if the line is vertical, kind of like this right here, then the slope of the line is what we would call undefined, sort of infinite steepness. And not able to put a finite number on something that has infinite steepness to it. And so as a result, we'll go undefined on that one. And you would see, of course, in the denominator, and I'll get to this piece momentarily, but what would happen numerically if we were to do our slope function, on our slope formula, on this right here, we would see that the denominator would be 0. And so as a result, cannot divide by 0. All right, so those are the four in terms of slope. Let's go ahead and get the equations, of course. Here we go. Let's just do the two more obscure ones, the ones that we don't see very often, but please know those in a little detail if you could, because they will come up. So talking about the equation of a horizontal line, there is a way to very quickly model a perfectly horizontal line because of something that they have in common, every single point. And obviously, an infinite number of points on this line, they all actually have one of the coordinates in common. So think about it for just a second. If I have a point here and a point here and a point here and here and here and here, which coordinate is the same if we are on a horizontal line? And if you kind of look at this, they all have the same vertical component to it. No matter what x is, they all have the same vertical piece to it. They all have the same y coordinate. And so as a result, if they all have the same y coordinate, then that's how it is expressed. And typically you see it as a b on the back, just for our purposes here, but it's just a constant. Y equals whatever the constant is. All right, good. Now let's go to the vertical line, the equation of the vertical. And by the way, this shouldn't be brand new. And if it is, slow it down a little and please ask questions about it. But basically, same argument. I would argue that every single point has the same coordinate on a vertical line. And the question is, which coordinate is the same? Well, if you look at this, it looks like I'm going horizontally the same number of units no matter where I am on that line. And if I'm going over horizontally in a constant fashion, then the x coordinates are the same. And so as a result, you'll see x equals a constant for a vertical line. Again, just kind of keep that in mind right there. That looks great. And then obviously what we'll talk about primarily is that slope-intercept form, which again, I know you have a lot of experience with, so let's just throw it in place. There's our y equals mx plus b. M, of course, represents the slope, and b represents, if you remember, just the y-intercept. All right, getting filled in very, very nicely so far. Hoping everything that you see so far looks good. Shouldn't be any algebra that you've encountered at this point that should be brand new, but again, if it is, no big deal. Okay, let's start just some examples. I think that's the best way to play it out here. And again, I will at least try to add some substance to it on the back, doing a little construction to get one conclusion taken care of. So obviously, guys, we know if we're talking about ranking the lines from sort of the most to the least in terms of steepness, it will boil down to slope. So just if you want, there's a 1 right there. Think about this one momentarily, and then look at all the other slopes if you get an opportunity. And I guess I'd ask you to just use a little intuition. Which would be the steepest line and which would be the least? So take a moment. See if you can order those for me. That'd be great. Maybe a 1 through 6 would be fine, something like that. Okay, well, here's what I have. It looks like the slope of 5 is going to be the biggest number there. So the bigger the number, the steeper the line. So I've got that one. It looks like number 2 would be this one right here. Let's see, number 3 looks to be this one. And just kind of working down, number 4 and number 5 right here. And then again, we've seen this now a little bit, but what is the slope of this line right here? Well, this is a horizontal line, y equals 2, and so it is a perfectly horizontal line. Oops. So as a result, it's the slope would be 0, and it's the least steep. You can kind of think about this in y equals mx plus b form. This is kind of a 0x plus 2. The 0x obviously is not written there, but again, you can see the slope is 0. All right, very good. Not a big deal, just getting us thinking about slope and measuring the steepness of a line. Hey, guys, not to be overly redundant here, but please try it on the negatives. What would be your intuition on which is the steepest, which is not, et cetera, et cetera. So on your marks, get set, and go. All right. Well, I hope you realize that it doesn't matter. It's really the numerical value that is going to determine it. The negative just makes sure that we're declining as opposed to inclining. So I hope you realize the order is the same. So get that in place. Let's move on. All right. So different variations on writing linear functions in y equals mx plus b. So let's just kind of get comfortable with this. I do it one particular way. If you remember it differently from Algebra 1, of course, do whatever works for you. Definitely not trying to reinvent the wheel with this lesson. So I just go y equals mx plus b all the way. Hopefully I left myself enough room to work here. But I literally write y equals mx plus b. And, sometimes I'll circle the m and circle the b and realize that those are the values that I have to put in place. And y and x are your variable quantities. So y depending on x, of course. And let's kind of go for it. In this case, it says write an equation for a line with the slope of 3 through the point -2, 4. So great news right off the bat, everybody. Slope is 3. That is m. So I'm going to use that, of course. Now, nowhere in the problem does it tell us the y-intercept. And so I hope you feel the same need as me. We've got to solve for the y-intercept here. And how are we going to do that? Well, the way I do it is we're going to use this point right here. If it is a point on the line, then it does make the equation true. And so we can use that to see what the missing component is. And the missing component, of course, is b. So that's the way I play it out. And then just solve for b here. Obviously, this is just 4 equals -6 plus b. And then as a result here, it looks like you're going to get a b value of 10. Got a little squished, but I think you see it in place. That looks good to me. And again, I use the slope, I use the x and y, and then I just solve for b. Once we have that, you could go f of x equals, by the way, I'll probably keep it in y equals for the time being, but how about a 3x and a plus 10? And there you go. Not too bad at all, right? Okay, let's do example 4, kind of the next level in terms of our variation right here. Write the equation for the line that passes through these 2 points right here. It's almost like an x1, y1 and an x2, y2. Unfortunately, when I kind of write my y equals mx plus b, I don't have anything to work with. I don't have the slope. I don't have the y-intercept. So I have to go find them. I think you all realize the slope comes first. So guys, let's just work off to the side here. And let's calculate slope. So y2 minus y1. I'll slow it down just to make sure everyone has the numbers correct. So it's change in the y's, y2 minus y1, over change in the x's. So 2 minus -4. So just be a little careful on that. I know you've done it dozens of times before, but make sure you do it perfectly here. -1 minus 2, -3, and 2 minus -4 should be +6. And so it looks like we get, as a numerical value, -1/2 is the slope. Beautiful. And now, guys, the nice thing about it, it just reverts back to the previous problem because my slope is -1/2. And quite frankly, you can put either point because now both points are on the line. So both points would make the equation true. So let's pick one and use it. I'm just going to use this one right here. Again, could use that one as well. But there's my x, there's my y, and let's solve for b. So shouldn't be too big of a deal right here putting this together. And again, if you know this stuff, you can just do some problems on your own here and just fast forward, making sure you're getting them right as you go through. There's, again, no real distinct need if you know what you're doing. It looks like this is +2. Bring that on over. I'm getting 0 here. And again, if you don't, just let me know. But I'm getting a y-intercept of 0. And so as a result, how does y equals -1/2 x sound? Good. If you want to go function notation on it, more power to you. F of x equals -1/2 x. Cool. Let's talk about just a couple others and one construction. We'll see if we can do it. And again, if you don't see the need, you can fast forward through. So guys, lines with the same slope are parallel, if you remember that from previous math courses. So parallel lines are always going to have the same slope. We'll probably see that come up a little bit in the future. But let's go ahead and kind of work with it in example 5 and keep this moving along. So write the equation for the line through 3, 2 and parallel to the line defined by y equals -1x plus 8. Now before I get into this one, I'm going to be visual with this one. It just sort of helps me seeing what's going on here. I won't even put tick marks in place, but I've got 3, 2, which give or take is about right there. So our line is going to go through that point, and it's going to be parallel to this line right here. So this one has a y-intercept up at positive 8, and it's kind of going down 1 over 1, down 1 over 1. So the rise over run is negative 1 to 1. So I'm going to just kind of do it like this. So it's going to go through this point and parallel to this line. And so as a result, I think we want the equation of that solid line that I am currently drawing right there. So just trying to get a visual perspective on it. Is it necessary? Nah, probably not. But I don't know, it helps me just making sense of everything. So don't overthink. Let's make it happen. Y equals mx plus b. Now the good news is, of course, our conclusion sort of speaks for itself. If these two lines are parallel, then you can see obviously they have the same rise over run, so they have the same slope. Slope of this line is negative 1. Well, guys, of course, the slope of our line is negative 1. No doubt about it. And, of course, you can see that this is your x and this is your y, and now we can use it. If it goes through the point, utilize it in the equation. Oops, sorry, I wrote the wrong thing there for a sec. So let's get that taken care of. Here's a 2, and plus the b. There it is. Sounds good. This is going to be negative 3, guys, right here. Add 3 to both sides, and I'm getting a positive 5. Now, again, as rudimentary as I drew this, I had this at positive 8 up here from right here, and you could see this intercept right here had to be positive below the 8, and we got 5. Perfect. I think we're in business. Y equals negative 1x. Add the 5, and there is your linear function meeting the criteria from the problem. All right, guys, 5 down. Parallel lines taken care of. Again, I would love for us all to do the construction of perpendicular lines. If you kind of know this, or if you're just not in the mood to pull this off, it's fine. I can live with that. But if you do have a ruler and a protractor, I think this is a great construction. I really do. And you can literally, you see it perfectly. So let's give it a try. So here's what I'm going to work with just in the space right here. And I'm going to ask you to just grab your ruler and give me just a horizontal line segment, something like that. Doesn't have to be too big, but something along those lines right there. All right, now, if you would, please place your protractor, pretty much in the middle, if you get a chance. Place your protractor in the middle and mark off 90 degrees going right up. Again, this is not a perfect construction, but it's going to be quite good. So 90 degrees right up, if you would. Mark that off on your protractor, and then, guys, I need a line segment kind of like that going through. Basically, long story short, this is going to be our x-axis and our y-axis of the coordinate plane. Okay, so you have that in place. Again, hopefully it's decent. And now here's what you're going to do for me. Grab your ruler, and I need you to put it along the positive x-axis, just a certain number of units. Keep it simple for yourself, and then highlight a line segment kind of like that. So however many units you want, really makes no difference, but keep the number in your mind if you would. So keep it nice and simple. So if you want to go like 2 centimeters, just keep it 2 centimeters and keep that in your mind. And you're going to label that A for me. So from there to there is A. Okay, so we have just this line segment running along the positive x-axis. Now, at the end of that segment, everybody, if you would, can you go ahead and grab your protractor and put it right there and mark off 90 degrees again from that point? So again, just from the end of your segment A, please go ahead and mark off 90 degrees. And then grab your ruler and go up a certain number of units, something different than what you did previously there. So a certain number of units, kind of going up just like that. And you're going to label that B. Keep that number in the back of your mind. So, I don't know, again, just making stuff up. If I went maybe 2 centimeters here, I don't know, maybe I'm going 3 centimeters up there or something, just something different. But everybody should theoretically have different results, and it's okay. All right, now, if you have A going here and B going here, that's the point I want to deal with along with the origin. And guys, if you would, grab your ruler, and let's draw our first of 2 lines. Yikes. Tough to do without the ruler there, but you get the idea. And guys, this will be line 1, right there. And what I need us to do is find the slope of line 1. And so let's get the 2 points that I'm focused in on. Guys, label that 0, 0 when you do get a chance. And here's the question. What is this second point right up there? What is that point? I went over A and I went up B. And so think about the horizontal and the vertical. What would be that ordered pair right there? Well, horizontal A and vertical B, I'm seeing that as A comma B. I'm hoping you are as well. All right, pretty awesome. We've got our first line in play, and let's go ahead and get the slope of that line. So M sub 1, the slope of line 1. And guys, just nice and simple, little slope, rise over run. I think we already kind of expressed that, but that's all right. I'm going to do the formula. Y2 minus Y1, X2 minus X1, and we get B over A. Nice. Really nice, as a matter of fact. One more line, guys, and as you can see, what we're going to try to do is make them perpendicular. So gear up if you can. One more time. Let's make it happen. So we've got the slope of our first line as B over A. Now what I need is the slope of the perpendicular. Here's how it's going to work, everybody. So do you remember we kind of start right here. And in this case, guys, I need you to go up A. And so go up A units, if you would, from here to here. So whatever this was right here, duplicate that going this way. Up A. And then I need you to put a point right there. Sorry. Let's just make sure we have that. Make sure I've got this taken care of. So if this was A, hey guys, that has to be A right there. Now mark off exactly 90 degrees. You might have to rotate your paper, but mark off 90 degrees going to the left. So protractor right there, going this way, mark off 90 degrees, and I need you to go B units this way. All right, there it is. So that is B units going that direction right there. So up A, left B. Make that happen if you would. And when you have that point, go ahead and give me a line going right on through right there. And that, of course, is going to be line 2. Okay. You know what I'm after, of course. What is the slope of line 2? So let's get that going in just a second. One thing to quickly note, and you see if you did this correctly, by the way, you know, my drawing is not ideal, but guys, put the protractor right in the middle there, and hopefully you do see that these two lines are perpendicular. That's the key. All right, now once we see that those two lines are perpendicular, I want to see the relationship of the slopes. And the key to this whole thing, I know it's taken a touch of time, but I think it's worth it. The key to the whole thing is labeling this point right here. So think about this. What is the horizontal piece? What is the vertical piece? And let's do it. Well, in this case, horizontal, it looks like I'm going over B units, but I'm going to the left. So it's really the opposite of my B. So if I went 3 centimeters, this would be -3. And then I'm going up A, so that stays positive. And so that's my ordered pair right there. Now, guys, slope it is, one more time, Y2 minus Y1. X2 minus X1. And you could see we end up getting A over -B, or really the opposite of A over B. So no matter what numbers you use, if you constructed this perfectly just like this, you created 2 perpendicular lines, these should be your slopes. And what is the relationship of those slopes? Well, number one, do you see that they are opposites of one another? And what do you notice numerically? They are reciprocals. And that's how we put it in. All right, again, it was just a way to give this lesson a little substance rather than just, you know, a quick Algebra 1 review. So opposite reciprocals. Now there is one, just real quick here, there is one exception to the rule. So for just about every pair of perpendicular lines, the slopes will be opposite reciprocals. What would be the one exception to that? And I'll just write it below here. If you don't want to, you don't have to. What would be the exception? Hey guys, what do you think about a vertical line and a horizontal line? What was the slope again of a vertical line? Undefined. What was the slope again of a horizontal line? 0. So you're not going to get that nice opposite reciprocal situation. Alrighty, good. Let's do example 6, example 7, round this out here. And one application, and then we should be all set. So example 6, write the equation for the line through to -3 and perpendicular to the line defined by this thing over here. It looks like it's in this general form, so I think I'll have to probably change that. So in order to talk about writing an equation for our line, I think we need to find the slope of this line right here, right? So let's go for it. I'm going to go ahead and bring over the x and the 6, not that the 6 matters a ton. And I'm going to divide by 2. And so I end up getting y equals -1/2 x and +3, something like that. So that's what I see as that particular line. I obviously now want to find the equation of the line through this and perpendicular to that. Again, I like being visual whenever possible. If you don't see the need, no problem at all. But here, guys, is 2, -3, right down here. And let's see, I'm getting y equals -1/2 x +3, so something like that right there. All right, looks good. And, oops, I'm sorry, I drew that wrong. Knew something just didn't feel right on that. I had something in my mind and was not quite correct. All right, there we go, -1/2 x. That's it. So it's got to be a declining line. My bad, just didn't feel right. And so now this is what we want. We want the equation of that line right there. Okay, we've got it. Here we go. Y equals mx plus b. Again, you can roll through this if you need to. M gets circled, B gets circled. We have to find them. Hey guys, if the slope of this line is -1/2, the slope of our line has to be +2. Opposite reciprocal. No doubt about it. Even you can see it with my cruddy drawing right here. Here's your x, here's your y. Let's go ahead and put them in place. Here's a 4 right here, of course. So bring over the 4 to the other side, subtract 4, and you've got your winner. And you could almost see it down here. If I made this +3 as a y-intercept, you know, give or take down here, should be at -7. And so I'm getting a y equals 2x minus 7. Again, if you're feeling good with this, great. Hopefully you're just doing the problems and working through. If you need further explanation, pause or rewind. But otherwise, just move through. Example 7. Write the equation of the line perpendicular to x equals 3 and passing through this point right here. Do you happen to remember what x equals 3 would produce on the coordinate plane? I'll write it here for us. It's a vertical line. So x equals a constant is vertical. Again, just to be visual, and then we can roll through this. There is x equals 3 right here. Go over x, 3, boom, vertical line. So we want it perpendicular to that and passing through 1, -4. So 1, -4 is about right here, give or take. And I want that line right here. Keep it nice and simple. No real math related here, just let's interpret. Obviously, the perpendicular line of a vertical is a horizontal. And a horizontal line is always defined by y equals a constant. I'll just go ahead and write that there. So y equals a constant. And what do we know about all the y values if it goes through that point? Well, if this y value is -4, then they all are. And so y equals -4. Wonderful. All right, that was quick. I like that one. All right, last one, guys. Let's put it all together. So just in terms of being a linear function, let's see if we can write a model for this and maybe utilize it a touch. So here's what I have. A tree was planted on Doug's property in 1970. In 1970, the tree was 18 feet tall. In 2005, the tree was 43 feet tall. And we will assume a linear relationship in the growth of the tree. write a linear model for the height in terms of the number of years since 1970. So we're going to have our dependent variable, height, in terms of time essentially, so the number of years, and so this would be the independent variable. Height in terms of time, I kind of like that, since 1970, that's great. And if you kind of look, basically we have a relationship of these two quantities represented as two ordered pairs. We already have a match here, independent and dependent. And so if you kind of look, here is an x, and here is a y, or an h and a t. So height in terms of time, in 1975, the height was 18. So there is our kind of x1 and y1, so to speak. I'm going to write that in there. Again, you don't have to if you don't want to, just kind of thinking out loud with this. And I also have a secondary match between the two variable quantities, which can be thought of as an ordered pair. Again, kind of an x2 and a y2, second ordered pair matching the two quantities, time and height. And so, long story short, guys, let's go ahead and put this in as two ordered pairs. I have year 5 in the model, 18 feet. So years since 1970, again, we didn't want to put 1975, we just wanted to put it 5. And then 35 years after the model starts, it's 43 feet. It would really be great if you could do a little math right there and come up with the slope, come up with the y-intercept, and let's do just a little interpretation, do a little prediction from it, and round this out. Okay, so I'm hoping you've done it already and you're just seeing if you did it correctly. So I would do the slope. I'm going to have to come down here, guys, to do the slope. But I get 43 minus 18, and then over 35 minus 5. Okay, sounds good. And when all is said and done here, let's see what we end up getting. I get a 25 over 30, which seems to be 5/6. All right, very nice. Got that taken care of, got the slope. Now let's use that slope and a point to come up with the y-intercept. So y equals mx plus b, guys. You did this already, hopefully. I'll try to be relatively fast for you. So I've got this piece right here, and then thinking that should work out pretty well, plus the b. Okay, let's see what I've got going. 25 over 6, 18 plus the b. And let's see, I'm getting, if I'm going to subtract this on over, I'll try to keep it, I don't know. I'll keep it as an improper fraction, at least for the moment. I'm getting a 108 over 6 on this end. And so 108 over 6 minus 25 over 6. Geez, I got 83/6. If you want to check that, quick mental math on my part, hoping you see that piece, which, again, I like just how we're going to interpret this. If you want to write 83/6 there, that's fine. I have no problems with that. If you want to go decimal on that, that's fine too. I kind of like a mixed number for this one, actually. And I'm thinking it's something along the lines of, let's see there, 13 maybe? Yeah, I'm going to go 13 and 5/6 on that. There we go. Something like that. Okay. Sorry for the delay. If you want to go y equals, that's fine. I like being variable appropriate with some of these, so height in terms of time, so I'm going to do mine as h. But again, if you want to do the generic variables, y in terms of x, that's fine as well. Guys, if you have some variation on that that is a slightly different answer than what I have, no problem. I have something like that, though. That would be the model for the height of the tree in terms of time. Okay, cool. Great math. I love that, that equation coming through, working nicely with two ordered pairs. Now, guys, let's interpret B and C. So what does the y-intercept represent? All right, guys. So what does that 13 and 5/6 represent? I tried to make it at least a number that would have some meaning. Now let's actually make the interpretation. What does that y-intercept represent, that 13 and 5/6? And if you look at the problem and its height in terms of time, the y-intercept always occurs when t is 0. Keep that in mind. And so what would it mean to you? Well, generally speaking, the y-intercept is really the initial value of the dependent variable, which is the height here. And so, maybe you can paraphrase if you want, but I see this as the initial height of the tree. Something along those lines. So again, I tried to at least write it in a way that would get you thinking in this direction. Don't know if I was successful or not. Hey, what does the slope represent? I like this 5/6, but what does it mean? All right, so we want to be a little careful with slope. Really, slope is rate of change. And what it really means, if we've used our formula correctly, it's change in y per change in x. So change in y per change in x. So it's really the increase in the height of the tree, because it's increasing, of course. It's a positive slope. So increase in the height of the tree in each year. Something like that would do. Again, if you want to paraphrase that, you're more than welcome to. So basically, how much it grows per year. All right, let's do just a couple quick calculations on this and wrap this on up. You guys are doing great. So it says, what is the expected height in 2010? All right, no big deal here. We have a model. Now we can use it to extrapolate. So the height in 2010, that would be 40 years. So I'm going to make T 40, and then that 13 5/6, or 83/6, however we want to play it out. But regardless, guys, let's go ahead and get that in. So just nice and easy, 5/6 times 40, and then plus 83 divided by 6. And there you go. That would be the projected height in 2010. So I have 47.17, give or take. And I think this was in feet. Okay, great. And last but not least, when will the height reach 100? So guys, in this case, I give you the value of the dependent variable. You give me the t value, the independent variable. All right, something like that would do. Let's make it happen again one more time. Let's let the calculator do the work on it. So here's what I have. Let's take that 100, subtract the 83/6, and then divide by 5/6. I'm going to do that up here, but remember, really, you should just multiply by 6/5. So it's up to you, of course. I'll just be careful on how I do it, but divide by that, and that's what I end up getting, about 103.4 years. So which would be, looks like 2073. Awesome. Again, it's just using the model to make predictions from it. Given the independent, find the dependent. Given the dependent, find the independent. Awesome. All right, guys, so just linear functions, the first family that we're really looking at, and really for the most part the math just comes directly from the Algebra 1 course. Hey, thanks for listening, and if something needs to be elaborated on, just let me know.